Okay, so last class we ended with getting number one started. It was about a record on a turntable. So I stood on the rotating platform. It's the same thing, okay? So if you watch one of my shoulders, if you were to paint one end of the record, what would you see happen, right? You would collect data. Probably video analysis is the best for rotation. And so we found SI unit, angular velocity, and then the angular acceleration, which by the way is the only thing constant in this problem, right? Is that it uniformly accelerates. So it's not a constant velocity, it's a constant acceleration. And then we found how many revolutions by first calculating the angular displacement with all of our new angular equations. Good deal on this part. So D does have a change, okay? It says if the record's radius is 15 centimeters, so now they give us the radius, how fast is a point on the edge of the record traveling after 0.25 seconds? And so the time is different. And so there is something that's going to be the same no matter what time you look at. What would you say? What stays the same? You can still talk to me. What's still the same at any other time? Speed, velocity, displacement, acceleration, right? That uniform acceleration. And so at a different time interval, no, we still have the same angular acceleration. And that was up above in part B. It was the 240 pi radians per second squared. How fast is a point on the edge? Maybe a visual would help. And so I talked about follow my shoulder, but here, what if we look at a top view of this rotating record and we look at just 1 point, okay? And so we know that once it gets going, yeah, there's an angular velocity, there's an alpha, there's an angular acceleration, right? And so at this 0.25 seconds, we have an omega quantity. We don't know what it is yet, but we have it. But they're saying how fast is a point. They don't really want the angular velocity. They want the linear velocity. And if you're like, the record's not moving in a straight line, well, the record's not, but for this really quick interval of time, isn't that point basically going to be going upward for this counterclockwise rotation? And we've seen this before with circular motion, yes? That tangent velocity is a linear quantity, okay? That's what we're going to be solving for here. And so VT, it's a tangent velocity that'll be our final answer. Now it actually is dependent on the rotation, which the final angular velocity at 0.25 seconds is different than at 0.5 seconds. So we'll also need the new angular velocity at 0.25 seconds. And so let's do that now. That one shouldn't be too bad. We're going to find it the same way we did earlier, just with a different time. And so we know angular acceleration is the same. So we can use that first version of angular kinematic equations. It's already solved for VF, so that's convenient. We can go back to the beginning where we started with no rotation, no angular velocity. And we know the angular acceleration is 240 pi. And now our new time is 1/4 of a second. And so if you look at 0.25 is 1/4, what's 1/4 of 240? 1/4 of 240, 60. And I'm going to keep that pi. And so our new final velocity, angular velocity at 0.25 seconds is 60 pi radians per second. Not our final answer. Are we good with that though? Okay. And so now that I know that 60 pi, how do I go from an angular velocity to a linear velocity? Why would they give us the radius? Okay. And so if we go back to the picture, put the radius on your axis of rotation there in the center of the record to that point on the edge is R. Isn't it true that that's a maximum distance for a point on the edge? Yeah. And so if you remember simple harmonic motion, we had a maximum distance and amplitude equation that does relate linear speed to angular speed. So in simple harmonic motion, we wrote it as V max equals A omega. But now we don't really have amplitude, but there's a radius. And omega, whether you move in a cycle or a circle, it's the same angular velocity. But this V max, you're going to get the maximum speed of rotation when you're on that outer edge. And so the linear quantity I'm going to put in is VT. So VT equals R omega. Now there is a way to derive it with arc length and theta. If you want, I can show you that another time. But since we just came out of simple harmonic motion, this is applied to circular motion. VT equals R times omega. Again, it's not on the formula chart, but this one you're going to use probably every day. Maybe not every problem, but we'll use it every day. So it should be muscle memory. It should come second nature come April 5th. What's going on April 5th? Our first rotation exam. Everybody good with that equation? All right, let's apply it. And so back to finding tangent velocity. We need that radius. They said it's 15 centimeters. Any thoughts on that? Boo, because centimeters is not SI. We want to move that decimal 2 places to the left. So it would be 0.15 meters times, well, that final angular velocity was 60 times pi. Let me make a little room here. And I'm going to keep the unit for a second. You know, I don't do this often. Truest physics, you should be putting units in and calculating the units. But my rule of thumb is start SI, end SI. You should come out. Now here, 0.15 times 60 pi. Now, this is kind of the norm. We're getting a linear quantity. All of August, September, we never put things in terms of pi, right? And so here I would say, let's get it out of terms of pi, go in and multiply it out. So what's 0.15 times 60 times 3.14? 28 point what? 26. Okay, so just, we'll say 28. I'm running out of room. What would the unit for this linear tangent velocity be? What's a meter times a radian per second? So if you remember from circular motion, radians is kind of a placeholder. You use it as needed. Do we need it anymore with linear velocity? No. And so it's going to be meters per second. Same old unit for linear velocity since August. So where does radians go? Well, it doesn't really cancel, but it's no longer needed. So it kind of just disappears. I'm not going to cancel it. It just kind of disappears. No longer needed. Good deal? So that would be our final answer. 28 point whatever meters per second. What if I was at a radius closer to the center? What if I was half the radius? I'd be going slower. They actually have the same, just like we said in circular motion, they have the same angular velocity. They sweep the same, quarter turn or half turn, whatever it is, relation of pi, radians, in the same amount of time, but it's their linear speeds that differ. Okay, So that's the record. Finish that out. Any questions on that first problem? Finding a point on the edge is kind of a good standard question. Okay, well, question 2 gives us a picture. It says a block hangs from a rope that's wrapped around a cylinder of radius 8 centimeters. First of all, how do we feel about centimeters? Boo, we got to convert it. So it would be 0.08 meters. After 2 seconds, the block, after 2 seconds have passed. So we started the timer at 0 seconds, right? And even though they don't say it, this block is going to move downward. What is the implied initial velocity? 0. So, kind of implied, VI equals 0. And now with rotation, we can also say angular velocity initially is 0. So it says we start the timer, we release it from rest, and after 2 seconds have passed, pause, the block has descended, fallen down 6 meters with a constant acceleration. Quit dropping my stuff. No free fall experiments with my calculator. And so look at what they gave us, 6 meters, linear or angular? Linear, that's a change in height, right? So we could say, maybe here's where it starts and there's where it ends. And so we have a delta Y of 6 meters, okay? And so we know it's going to fall 6 meters. Now they don't tell us the acceleration because A and B. A, what is the block's acceleration? And then B, angular acceleration. And so notice they gave us quite a bit actually of linear quantities. We're finding the linear acceleration in A and the angular quantity in B. Typically, they don't say linear acceleration, but if they want angular, they'll say angular. And so good old kinematics, right? Good old fall semester. How are we going to find linear acceleration? Well, we know it starts at 0. We know 2 seconds are going to pass. And we said there's a height change of 6 meters. Now it did say it descends. So let's talk. It's falling down. Is the acceleration 9.8? Why not? It's attached to a string. Objects falling at 9.8 meters per second have no strings attached typically, right? It's free fall. The only thing working on you is gravity. So it's not 9.8. Just because it's falling down doesn't mean it's in free fall. But this descending, it's falling down. If you're a stickler for signs, you might say it's in negative direction, right? If you go with the standard, it's falling in the negative direction. But watch, kind of get your mind in that other way of thinking. It's going forward 6 meters. Is it okay if I call this forward direction positive? It's not the norm, so I'm going to do that. I'm going to say down is the positive direction. But if it makes you feel better to say negative, then your displacement has to be negative and you'll get a negative acceleration. Okay? So it's kind of up to you. If they don't define the positive direction, you get to just be consistent. Yeah, you can choose down as negative, but then you'd have to make the displacement negative and your answer will come out negative acceleration. But me, with pulleys, with forces even, I started changing in October. I was like, let's just make forward positive, right? And so that's what I usually, that's my rule of thumb. By the end of the year, forward is positive, but either way. So with me saying down positive, then I can use a positive 6 meters. And we're looking for linear acceleration. And so what good old September kinematic equation are we going to use here? The second one. And so that delta y equals VIT plus 1/2 a t squared. VIT goes away. Y'all know the drill. We're kinematic pros now, right? Don't we love kinematics by now? That's going a little far, Miss Earhart, right? Okay. So 2 squared is 4, half of 4 is 2, 6 over 2 is 3. And so we get a positive 3. It's accelerating in the forward direction, 3 meters per second squared. That's what they want. That's our final answer. Now B, angular acceleration. Question. Well, if I say I went with the sign convention, down forward is positive, so it's going to accelerate in the downward direction. Now, if you say down is negative, you should come out with a negative acceleration because you would have to make your displacement negative. Okay, so tomato, tomato, I don't know what the key does and who's right, who's wrong. As long as we both specify our positive direction, we can both be right. Okay, by the way, AP exam in 49 days, they usually define the positive direction. Okay, if they don't, then you can. All right, B. Before we solve B, let me give you a new phrase. Assume the rope did not slip, AKA, this is non-slip condition. Now, I haven't said this phrase yet exactly this way, so I'm going to kind of demonstrate. Video people, follow the verbal. And so, now I'm not going to waste my paper towels, okay? So you're just going to have, you know how toilet paper, you know how paper towels work, right? I'm not going to actually put a block on this. Are the paper towels really a rope? No, but it can be rope-like, right? And so here, they said they wrapped a rope around a cylinder. They attached a mass. I'm just going to pull on it. And so we know it's going to accelerate down. Now, what's this non-slip about? Well, have you ever had maybe, the cat or kid, brother or something pulls all of the paper towels or toilet paper out and you have to rewind it, right? Do we always get it a tight wind back up? No. And so there might be times where you pull, but it doesn't rotate. And for this, I'm actually going to switch over to an actual rope. Now, I don't have a cylinder. I got a water bottle. It's not really water, it's green tea. Ignore that part. Okay, it's a round object that's going to rotate. Yes? Okay. And so I'm going to put a rope on it and I'm going to wind it so that I get multiple, and I got to hold it. Usually you have glue or something to get the end, but you don't have to. Right now, no glue. I just overlap the rope. What's holding it in place right now? No tape, no glue. What about the rope? Because this mass should want to fall. Friction. What kind of friction? Static, AKA gripping friction, right? So the rope has gripping friction with itself. And I'm going to say with itself because this water bottle is pretty slick, right? But if it's, a tube of paper towel, they're a little rougher. Now, what will happen as this begins to fall? Well, watch this. If it, so here's the knot. If it unrolls one full circle, how much of the rope goes down? The knot went down, how much? One full circle unwinds a distance of the circumference, okay? So the cylinder rotates one revolution, one circumference. The rope hanging down with the object extends, descends, equal to that of the circumference, yes? And so this linear displacement came from one full rotation circumference. That's assuming gripping friction played a role, okay? So I'm going to try to demonstrate what happens if you slip while turning. And so if you slip, maybe there's a time when it slides down but doesn't rotate, right? So I'm going to have more linear distance than rotational distance, yes? Or not so much maybe here. I mean, we get some ice, but if you're driving in the snow, maybe you get stuck in the snow. Like I would get stuck in the mud at the farm, okay? Sometimes your car got stuck. And what that means, you're not moving. The wheels are turning, but it's not moving in linear motion. So that's not when you have gripping friction, that's where you're slipping. Now for the next month, I'm going to be saying rotating without slipping. I'll say non-slip, okay? And this is actually unique. The math is easier when you have non-slip. And so what does all this mean? Watch it, watch. In terms of your rotation of the cylinder and the box descending, it means the displacement, vertical displacement here of the box in one revolution is equal to 2 pi r of the cylinder. Does that make sense? We get the 2 pi, one cycle, one rotation. Hopefully we've embraced 2 pi by now. Well, here they want acceleration. Well, that equation that we used earlier, connecting linear velocity to angular velocity, Vt equals omega times r, is considered a non-slip equation. And what would be the equivalence for acceleration? It would be omega times, oh, no, not omega. What's our Greek symbol for angular acceleration? Fish, alpha, times radius. And the units for both work out. Radians per second squared times meter gives you meters per second squared. And so these two equations are going to be super duper handy for rotating objects under that non-slip condition, which I would estimate, if there's a calculation to do, 99.9% of the time, it's going to say non-slip or equivalent. Maybe they ask you a concept about slip, and really there's forces and energy at work. So we'll be doing this one for the whole month. But there's your teach piece about what non-slip indicates, okay? It means you translate, you have linear displacement equal to the circumference of one rotation. Or if you make two rotations, you have that equivalence, okay? Mm-hmm. No, it's either or. I'm not trying to put them equal to each other. So they're derived equations. I had used that simple harmonic motion for Vmax to get the first one and just showing you kind of the equivalence, but for acceleration. So you can use like arc length and get into dividing them by derivatives, dividing by time, each quantity. So, that velocity tangent is going to change if you accelerate. So the derivative would be the acceleration. And same thing with your Greek symbols. Divide both sides by time, and you should end up with this same equation. Does that help? Okay. And so for this problem, what are we going to use? We're going to use that acceleration one. We know linear, we now know radius, and so they ask us to find the angular acceleration. And so angular, I'm going to solve it, isolate. It'd be that 3 meters per second squared over the radius, someone get calculator ready, 0.08 meters. And so calculator, get ready. If you're not using a calculator, look at units. What happens with our units? Does it become meter squared over second squared? No, I got meters in the numerator of both fractions, if you will, m over 1. And so meters is going to cancel. What does that leave us? Something over second squared. There's no physics variable there. So what's our placeholder unit that comes back to us as needed? Radians. And if you remember the other day, we said the SI unit for angular acceleration is radians per second squared. Number people, calculator people, what do we get? 30 over 0.08. $37.5. Okay. Good deal. And the people not doing physics, they're telling themselves right now, I'll get it by April 5th. I'm not doing this problem again. Oh, but you're recording. I'll watch it later. Okay, because I'm watching. I know who it is. Hi, thank you. C, what's the angular velocity of the cylinder after 2 seconds have passed? And so now that we know the angular acceleration, and that said that was going to be constant, so I'll have 37.5 radians per second squared. We know the time is 2, and it's still going to begin at 0. Now to solve for final angular velocity, what kinematic equation do we use? You can turn back to page 1 where we put all 3, or you can look on your formula chart. There's 2 of them there. Notice we don't know angular displacement. So we got to pick the one that doesn't have angular displacement, delta theta. The first one, yes. And so omega F equals omega I plus fishy T. Omega I is 0. And this one's nice since it's already solved for. And again, I'm going to put my units in. And so 37.5 times 2 is, calculator people, 75 units. What happens with units here? Radians per second squared times a second. One set of seconds cancels. And so we're left with radians per second. Is that what we should have for omega final? Yeah, so it works out. Everybody good there? Thank you so much. See you tomorrow. All right. D, through what angle? Now, I know what you're thinking. Angles, degrees. Here, embrace the radians, okay? Through what you can report angles as radians, right? 180 degrees is how many radians? Pi, 1 pi, right? And so you can report it either way. And with rotation, I know that we've been in degree mode on our calculator all year long, and I still encourage that, right? But let's report it as our radians. So what number radians? If you want to convert that to degrees, you could, but you can just at minimum solve here. And so how many radians? What's the angular displacement that it rotates in 2 seconds? And so embracing our rotation, and it's the same time. And so we can use the givens from above. How do we solve for delta x? I'll accept one of 2 equations. The second one is probably the most popular because it's typically already solved for delta theta. And so it's that omega IT plus 1/2 angular acceleration times time squared. The other is that third one that's not on the formula chart, but when you substitute your angular quantities in for your linear quantities, it does have a delta x. You could, a delta theta. You could use it. Okay, so we plug in. Again, this thing, t equals 0. It's not rotating, so no initial angular velocity. And so it's just 1/2 of 37.5 times 2 squared. 2 squared is 4. 1/2 of 4 is 2. What's 2 times 35? 37.5. We're back to 75 again, but now our unit is radians, okay? Should I memorize that, oh, the final angular velocity and the angular displacement are always the same? No, I would not. Okay, sometimes magic of math happens. Coincidences do happen, right? And so we'll just end there. Or maybe tomorrow's question says, how many revolutions does the cylinder make? If I know the angular displacement in terms of radians, could I take it one step further and find out how many revolutions it makes? Right. We got our conversion factor, 2 pi radians on bottom, 1 revolution on top. Do it for me. What's 75 divided by 6.28? So here's where you can test your calculator. Do I need parentheses around 2 pi or not? Or just multiply in your head. So how many circles or revolutions does this cylinder pulley system make? And it's so close, just round it. 12, right? 11.9 something. And so we'll say about 12 rotations or revolutions. Okay. Again, they didn't ask us, but they could have asked us. There you go. All right, question on like a basic pulley. I mean, we didn't do later, we'll be doing pulleys with forces and torque. We'll be doing them with energy. You'll see pulleys for the next month. Yes, so in October, we said it was a frictionless pulley. And so that would be like my cylinder, the rope just slides across. And if it's frictionless, then it's super smooth. There's no heat loss. There's no turning of it. But now you'll see our questions with the phrasing that, what's the official phrasing? It has mass, that comes later, and it has friction, okay? They won't say it's massless and frictionless. That's what they'll do. They just won't say it's frictionless, okay? And by the way, I think last year or the year before, there was a pulley question, and it started part 1, massless, frictionless pulley. And then by the end, like part D, it said, now imagine the pulley has mass and friction, okay? And so then you had to do rotation to answer it. Okay, the last one on page 2, we got a bowling ball. Now, I'm not a professional bowler. I bowl like once a year. So don't take, anything I say like, oh, this is going to win me championships. We're looking at a simplified version more than likely. A bowling ball has a diameter of 30 centimeters, a diameter. Yeah, we've been talking in radius terms. So it's got a radius of 15 centimeters. So 0.15 meters. So watch 2 things there. Read carefully, y'all. It's tossed down a lane with an initial backspin of 30 RPM. Now, AP probably won't just say RPM and expect everybody in the world to know what RPM is. Hopefully you do. What is RPM? Revolution or rotations per minute. Do we want minutes? Do we want revolutions? No, we want radians. So this is a way to give the rotational speed, but it's not the SI units that we want, okay? And so we'll end up converting that here in a second. It's not as quick like move a decimal. And then it says that there's friction. Now they grease the lanes up, they are slick, but there's still some friction. Gives the ball a forward angular acceleration of 5 meters per second squared, radians per second squared, until it hits the pins 6 minutes later. Now they show a picture of the bowling ball or a ball initially and finally. Look at your directions there. So the directions, it starts out with the backspin. Notice that's the counterclockwise direction. And then it ends going in the forward clockwise direction. Do they specify which rotational direction is positive or negative? They don't. But do you think it's important that we distinguish direction differently? Yes. So we get a choice, and I'm going to let y'all decide. I don't know what the key says. I haven't looked at it in a year, okay? But do we want to start in the positive with backspin being positive? Or do we want to end with forward direction being positive? End with positive. That's what I would probably, I like to end on a positive note, right? That phrase. So I'm going to make clockwise the positive direction. And so anything with a backspin would be the negative. So technically that initial backspin of 30 revolutions per minute, I got to make it negative. That acceleration, angular acceleration that they say is forward, that's going to be a positive 5. Now, radius and time don't have that direction, so that's fine. Everybody good on direction? And if you are saying to yourself that, no, I want to start in the positive, go for it. Okay, we should still get the same magnitudes, just opposite signs. Okay, how long did it take for the ball to begin rolling forward? Or rephrase it, how long did it take for the ball to stop rolling backward? Okay, it's the same thing. It's this transitional speed. And so I'm going to add a little picture here just in case you need more visual. So here's my very fancy non-symmetrical bowling ball. Oops. It's going to start out with negative angular velocity. It's going to go down the lane. Notice, do they tell us how long the lane is? No, we could figure out circumference since we know diameter and radius, right? But we don't know how long the lane is. And I don't know if that's standard. I don't have it memorized. I'm sure we could Google and get an average, but we're not gonna. And then the pins are down here. And so from start to finish, we know this is 6 seconds. When's it gonna quit spinning backwards? Should we assume at 3 seconds, middle? No, but we should know that it's gonna be somewhere in between beginning and end. So I'm just gonna put it right here. Okay, and so this is where it comes to a split second angular velocity of 0, just for the moment. So it's final for the backspin portion, but initial for the forward spin motion. It's the moment that if you were to slow motion footage this, you would ask yourself, is it rotating at all? For that split second, split microsecond, it's not. It comes to a split second stop in the angular direction. Okay, and this is the time we want. We want this time. Well, I don't know the forward spin time, and so we got to do some kinematics, rotational kinematics. But first, maybe we should convert that 30 RPMs, okay? So I'm gonna go on the side here. So 30 RPMs, yes, it's negative, revolutions per minute. We want to get rid of minutes and go to seconds. So hopefully you remember 1 minute is equal to 60 seconds. I'm going to do a double conversion. We want to get rid of revolutions and go to radians. So 1 revolution is 2 pi. And so what cancels? Minute goes away as a unit, revolution goes away, and we'll be left with radians per second. And notice, multiply the top, 30 times 2 pi is 60 pi, divided by, hey, look at that. What do we get? Pi. Now I'm gonna go in and show a 1, because I don't want anyone looking back at this saying, did she just forget to put the number? No. There's an understood 1 there. I'm going to literally put it. And don't forget, it's what sign? It's negative. So this is the initial angular velocity. And they want to know timing. And so we know initial angular velocity. We've already concluded that the final of the backspin is going to be 0 velocity. We're looking for time. We know angular acceleration is positive 5. That same first equation again. And so omega F equals omega I plus alpha T. So 0 equals -1 pi plus a positive 5 times t. And so t is going to equal what? Now, by the way, do we keep times in terms of pi? Does that make sense? Now, so let's go on and take it out. So you got to add 1 pi to the other side. So 3.14 divided by 5 is, if you're sleepy, be my calculator person. Sorry, I woke you up. You get what? 0.628, so we'll call it 0.63 maybe, is how long it takes. Now, if we wanted, could we now find the time it takes to spin in the forward direction till it hits the pins? We could, 6 minus, right? Now I say could. B says, what was the angular velocity when it hits the pins? And so we're looking for VF at the pins region. We have 2 options here. We can pick up where we left off, or we can go back to the beginning. We have enough information for either. So what do y'all want to do? Very beginning or pick up where we left off? Pick up where we left off. So to pick up where we left off, we just care about the forward spin. And so now omega I is going to be 0. What's the time of the forward spin? What do we got to do? 6 minus 0.63. And so we'll get 5.37 seconds. Now, what's the same in both segments? They said it was a constant acceleration. And so we know alpha is still going to be that positive 5 radians per second squared. So what popular equation are we going to use? Same old first, right? Again, there's no mention of angular displacement or displacement at all. And so omega F is actually what we're looking for. And we're just doing the forward. So maybe if you look at the key, it goes back to the very beginning, but we should get the same thing. So for the forward direction, omega I zeroes out. Alpha is 5, time is 5.37. So a little over 25. What do we get? It comes out a positive 26 point what? Okay. 0.9, maybe just 27 radians per second. Okay. I don't mind rounding the 0.9s, right? So truth, you won't have much math in free response. Okay, so there's the first thing. If there's a numerical response, 2 or 3 digits. So either one of these would be fine. Basically, you don't want to round too much, don't round too little, don't put 10 digits from the calculator, right? And so that's the rule of thumb, is 2 or 3 digits, okay? If they ask you a sig fig question, which notice how often I've talked about sig figs, very rarely, right? Today could be day 1. If they ask a sig fig question, it's going to be in multiple choice, more than likely, but it's rare, okay? They don't want to, knowing sig figs isn't really physics. They ask you more physics questions than technical math or science questions like that. All right, so there is rotational kinematics worked out. Not that it's every single problem available. In fact, page 3, I highly recommend that you try some of them as independent practice, okay? In years past, I only had 1 page of kinematics because it was like, oh, this is easy, move on. But then students were like, oh, can we have more practice? And so here's a second page, extra practice for you, rotational kinematics. Do it at your leisure, right? So now we're going to spend the rest of class looking at torque. Now, torque is a huge topic. We're going to start baby steps. Last class, I pulled on the cabinet door, right? And let me just go back to our equation so we have a visual. So notice I'd switched colors because torque is something that kind of takes forces further, okay? And so I can exert a force on a door. Maybe I push at the hinge. Do we open doors by pushing on the hinge? No, in fact, you're probably not going to open it at all. You might break the hinge, have linear motion, but you're not going to rotate the door open. And so it's about not just the force, it's where the force acts on it. So we usually open the cabinet door or any door furthest from the hinge. But remember, it doesn't have to be. I can go to that midsection of the door and pull a little bit harder though. And so the difference is that lever arm. And so just a reminder how you define lever arm. It's not always horizontal. It's not always vertical. It may or may not be the radius of a circular object. It may or may not be the full width of a cabinet door. It's from axis of rotation, AKA the hinge, to the line of action, also known as where the force is, right? And so that's how we're going to use lever arm on page 4. Again, baby steps. All we're doing in number 1 is identifying lever arms. Now you see a bunch of arrows, you see the graph and you're like, Ms. Earhart, are we gonna graph? Is this slope area business? No, it's just a grid line for reference. Each grid line is gonna be 1 meter between. It says, find the lever arm about the origin. Tomorrow's question might say, about the left end of the meter stick. That's gonna be where your origin or your hinge or your fulcrum or your axis of rotation, gosh, it's got so many terms, right? And so axis of rotation, hinge, fulcrum, pivot point, okay? Y'all bear with me, I get this joke once a year. Pivot, pivot. And today's generation doesn't understand that joke like students 10 years ago. Anyone know that one? Friends. Someone last period said, Friends isn't funny. And I kicked them out of class, metaphorically. Okay. So it's the pivot point. It's the fulcrum. That's a new word. It's the hinge about the left end of the meter stick, right? What if I hold the meter stick on the right side and say about the right side of the stick? Can I still rotate a stick if I hold it on one end? Yes. Or I could hold it in the middle, about the center of the meter stick. I can rotate that. Couldn't I hold it at some odd number? I'm even covering up, maybe you don't see it. Okay, can't I rotate about some in-between distance? And so this whole about the origin, this is your reference point, your hinge, your fulcrum, it has so many names, your pivot, or how we put in the definition, it's really your axis of rotation. I only give you the others not to confuse you or stress you out. Different problems may have a different, like a door problem might say the hinge. A teeter-totter might say fulcrum, okay? If I'm a basketball player rotating my body, I might be about 1 foot, the pivot, right? Okay, but number 1 is all about the lever arm. Now, this is going to be a little different for us. It's not necessarily AP, it's not the norm. It's just the spirit of lever arm. So work with me here. I'm going to go in order. A is in the quadrant 2. If you look, it's a force, it's an arrow. Lever arms are not arrows. It's a scalar distance. And so later it's going to tell us these arrows are forces. Can we go in and get the magnitude of the force now? FA is 2 grid lines, so we're going to say it's 2 newtons. Later we'll be doing torque, so we kind of need both of these. And so what's the lever arm for vector A? Now here's where we got to, identify it with the axis of rotation. And so I'm going to put just a circle as a visual on the origin. And you don't necessarily have to connect the two, because maybe this force is literally where it is, or maybe they're just showing us the direction of the force. But it could be anywhere on this line of action. So this is our line, and I'm trying to write big so y'all can see it over the grid line, of action. or called line of force. So I just extend the force. Everybody good? Now, can we identify for this vertical force the perpendicular distance from the axis to the line of action? Do you see it? It's a vertical force, so the lever arm has to be what's perpendicular to vertical? Horizontal, from the axis of rotation to the line of action. And so I'm connecting that origin point to the line of force. This is your perpendicular lever arm for vector A. Count the boxes, and being horizontal is nice. 1, 2, 3, 4, 5. So the lever arm for vector A is 5 meters. Well, it's to the left of the origin. Do I need a negative? No, lever arm is just a distance. Okay, we'll do direction of torque later. Everybody good on A? B is actually down below. B, let's get the force because we'll need it later. It's easy just to do it now. Mid-grid to mid-grid, what would we call the magnitude of the force? Thought. 5, 4 complete and half. So 5 newtons. But really, we want right now the lever arm. And so it's a horizontal force, meaning I need a perpendicular, vertical lever arm. So we're going to extend the line of force. And usually I try to go towards kind of the region. Okay, so the origin's on the y-axis, so I want to go towards that. But true story, you may have to extend it to the left. And so this is our line of action. Line of force. And now I'm going to draw in our vertical lever arm from the axis of rotation to the line of force. And this is our perp B. Thankfully, it's nice with the grid lines, so count it up. We get a lever arm magnitude of 8. Well, it's below the origin. Should it be -8? No. Lever arm is just a magnitude, scalar, distance, quantity. Good deal? Okay. If you're bored with that, I hope so, because honestly, it's not any easier than that when there's straight vertical, straight horizontal, okay? Now, C and E are actually easier. What's unique about C? The force of C is hard to count, so I'm just going to say big. The lever arm for C is the easiest on the whole entire page. Line of action, well, it goes straight through your axis. So if you push at the hinge, what's your lever arm? 0. If you're measuring from the hinge, but you push on the hinge, it's 0. So later when we go do torque, I don't need to actually know the measurement of that force because it has 0 lever arm. It's going to have how much torque? 0. So yeah, you might move the object linearly, but you're not going to rotate the object. Everyone good on C? Now we'll come back to D. D is actually the trickiest one of all of them. But E, well, it's not touching the origin, but if you do your line of action, what do we notice about E? The force, I'm going to say, is moderate. And again, it's not going to matter because the lever arm is what? Your line of action force goes through the axis of rotation. So to measure the distance between the axis of rotation and your line of action is 0. So it's just like C. Maybe instead of pushing on the hinge, I throw a ball on the hinge or something. I don't know. That force is going to happen at the hinge location. No rotation, no torque. Everybody okay? D is going to feel a little different. And FYI, we're going to end up doing geometry, similar triangles. So angles are going to be here, but similar triangles will save us. And so D is this northwest vector. So if I extend line of action, I really don't need to, because can I go ahead and draw a perpendicular distance from the axis of rotation to the line of action? Now I'm going to erase those blues because I don't want to confuse things. And you don't have to do it perfectly. But isn't this a perpendicular lever arm to that given force? So technically this is our lever arm for D. Now that's not nice with the grid line, okay? It's not nice with the grid line. And so I'm going to kind of zoom in here and work on this side. We're going to do some similar triangles. So do you see a triangle right now? So the triangle I'm talking about is this one. I'm going to draw on the side. I'm going to keep the solid line, my actual lever arm. That's our answer. But here's the triangle. And maybe I identify this angle at the bottom right. It's similar to a force triangle. Remember, the arrow is your force. And so to share that angle, can't we draw the force with components? And there's that shared angle. And I bring that triangle up because we can easily count the grid lines of the components. So the horizontal component of the force would be 1, 2, 3 base and a height of 4. And we get a nice right triangle in our force, 3, 4. So can we answer the question, how big is the hypotenuse, the force? It's 5. It's going to be a 3, 4, 5 right triangle. So there's our force value. We didn't use the grid line to measure the exact force, but we used components, Pythagorean theorem. And so now, if those two are the same angles, notice the lever arm is the opposite leg from theta. So look at your force triangle. Which component is opposite theta? 4. And so this one is 4 meters. Good deal? Now you could count on the grid line. That base is 5, and it should agree with the similar triangle of the two. Okay, so that one was a little trickier. Does that mean all AP questions are going to be like that? No, but the occasional, yeah, maybe some angles. All right, well, let's use these forces. Oh, we need to write them out. So we got 4 meters there, and then 0 meters on C and E. And then B was 8 meters, and A, 5? I think it was 5. Now, part B says, assume the vectors, the forces above, are in proportion to their arrow length. So I had us find those forces all along. Rank the torques from largest to smallest. And we're going to go on and do all of them. I mean, why leave one out? And so for A, we said the force, torque, is force times lever arm. And we had a force of 2 newtons times 5 meters. And so we get 10 Newton meters. Final answer? Or do I need to simplify the Newton meter? Is that a joule? I hope I had this unit discussion with y'all last time. Did I? Did I not? I'm going to guess not. Note to self, torque is not energy. And so this is not equal to a joule. In January, when we did work and energy, we said, oh, force times distance is work. Newton times meter is energy, right? Joules. However, torque is not energy. Rotational energy comes later. This is not energy, so it does not equal a joule. So we'll keep it as 10 Newton meters. Rinse and repeat, do the same thing for each one. So B had a force of 5. So 5 newtons times 8 meters, we get 40. It's plug and chug from this point on, right? C had a force of big times 0, so we get a torque of 0. Now you know why I didn't waste time trying to measure the distance there, the force magnitude. And then E, leave a little space, had maybe moderate force times 0 lever arm, so it's got 0 torque. D, we use similar triangle to know, and Pythagorean, 3, 4, 5 newtons was the hypotenuse of our force triangle times the lever arm of 4 meters. So 20 Newton meters. So is it whoever has the biggest force has the most torque? No, C had no torque whatsoever. And so your final ranking would be B is greater than D, greater than A, greater than C, equal to E. Good deal? Okay, so that's not really a typical setup for a torque problem, but it was just to help us measure out lever arm. And so the next page, we'll hopefully get at least one done, one today, one next time. We got this meter stick. It says find the mass, comma, force, comma, or distance needed to balance the torques. Balance, equilibrium, Newton's first law. Maybe we need a little lesson. Last time I gave you Newton's second law as it applied to torque. When you have a net torque, that's how we get an angular acceleration. But what if everything balances? So Newton's first law, when we did forces, it was that forces balance, right? Net force is 0, acceleration is 0, right? It could be an object at rest or an object. What was the other situation? Constant velocity. I'm kind of making a table here. Then we also have, and I like to spell torques with the symbol for torque, because why not? And so then Newton's first law actually works for torques as well. This is when net torque equals 0. Instead of linear acceleration equaling 0, angular acceleration equals 0. Well, this can be true for objects at rest, so no rotation, or couldn't you be rotating at a constant angular velocity? At constant angular. So something can rotate at a constant angular velocity and still be considered in equilibrium. Again, the comparison, Newton's first law for old school linear forces, and also now with torques. And so we're going to do balance of torques with A. We're going to do A first. And it tells us more that the rod itself that all these masses are sitting on has a mass of 4 kilograms, okay? And so what is this about? So here's my meter stick, okay? Normally, where do I balance the meter stick? No masses, where should I balance it? In the middle, 50 centimeters, right? 50 centimeter mark. Well, what happens if somebody comes along, okay, and puts an additional mass on the right side of the stick? When I let it do its thing, what's going to happen? Okay, that mass brings the right side of the meter stick down in a clockwise or counterclockwise direction? From your vantage point, this that I'm doing is clockwise, okay? I know. And then what if I put the additional mass on the left-hand side? Now we're going to get a clockwise or counterclockwise? Counterclockwise direction. And so, and by the way, what if I put the mass not at the end? Isn't it still going to lead to a counterclockwise? So it's not about just the force, it's about where you put the force. And so this one, by the way, this is the experiment that, usually we have students do. We've got meter sticks, we've got hanging masses, find the balance point using physics, right? And so just imagine I give you meter stick and masses because we're not going to have time for lab. Sorry. Okay. And so we've got a 2 kilogram mass. It has a gravitational force, right? Now I'm going to try to stay in symbol form, but we have FG2. If you want to call it ABC, you can. I'm just going to go with the number as the subscript. Well, this force is going to cause what kind of rotation? Well, it's on the left side. Oh, look, I see a triangle. What's the triangle? So typically, y'all, the triangle just means fulcrum. But you can, lump it all together. This is the axis of rotation. This is the pivot point. This is the teeter-totter middle part, right? This is the, what other word is it? This is the hinge. It's got a lot of different names, okay? But usually when they give a triangle, I don't know why, but it's called a fulcrum. And so here, I'm on the down left side of the fulcrum. It's going to cause alone what kind of torque? Kind of visualize if this mass alone led to the rotation, it's going to rotate in the counterclockwise direction. Yes. So would you have to use torque in this, or could you just do it? So you could do, yeah, some of these you can use a center of mass equation. Sometimes you're able to do forces. Sometimes I'm taking a torque approach because that's what we're learning, yeah. But yes, I think center of mass would work here. Now, I will tell you later on, when you're solving for an unknown force, I don't know if you could do center of mass on that one. Okay, but yeah, I'm going to use torque to find this one, okay? Now, one last thing to find about this 2 kilogram, what about lever arm? Where's the lever arm for the 2 kilogram? So it's from your axis of rotation to the line of force. A vertical force has a horizontal lever arm. And so our perp for the 2 kilogram would be what distance? 5, 0 to 5. You're looking at the positions, right? And so 5, we'll say it's meters. We'll keep it SI. We'll keep it simple. Good with the 2. Now let's rinse and repeat. Let's do the 6. 6 kilogram maybe has an even bigger force, right? So FG6, well, it's still a down force on the left side. And so if you were to imagine it wrapping around the pivot, it's going to rotate also counterclockwise. What's the lever arm for the 6 kilogram? Well, it's from your axis of rotation, your fulcrum, to the line of force. So you can literally draw it to that gravitational force. If it wasn't lined up, you can do your extension of your line of action. And reading those positions, our perp for the 6 kilogram is what? 1 meter. And then we have an unknown mass all the way on the other side. So I really don't know how long it is. So I'm just going to say FGM. Okay. Notice it's a down force on the right-hand side, which leads to what type of torque? What direction? Clockwise. And so notice you may be wondering, well, how do you know what direction? Kind of try to wrap around the pivot point. Because if you look at the meter stick, Okay, my pivot point right now is in the middle. One end that moves down is kind of wrapping around that pivot point. Okay, it's not going to wrap away from the pivot point. It's wrapping around that pivot point. And so that's a clockwise direction. Last thing, the lever arm from your axis of rotation to the line of force, vertical forces, horizontal lever arms, and our perp for our unknown mass is going to be what? 4. Everybody good identifying? Now, if you're thinking, Miss Earhart, you're making this too hard. Isn't it 8 kilograms? 2 6 on the left. Shouldn't it be 8 on the right? Location matters. It's not going to be 8. And so now we need to apply Newton's first law. And so that net torque equaling 0, or you can say torque clockwise balances the torques counterclockwise. This is actually where I start most of my equilibrium statements. Well, who's torquing clockwise? The unknown mass. And so I'd have FGM times the lever arm of M. I'm not putting numbers in just yet. Bear with me, variables. Well, I can do one more thing with that FG equals mg. And so I have an unknown mass times gravity times its R perpendicular, its lever arm. Okay, switching colors. Now that's our only clockwise torque. So now equals who's going counter? Well, I'm going to do the 6th one first since it's on the same screen. And so FG of the 6 times the 6 lever arm. FG equals mg. And again, 6 is the mass, but I'm trying to stay variables for now. But that's not the only counterclockwise. We've also got that 2 kilogram. And so plus FG2 and its lever arm, and M2G and its lever arm. Well, what do you notice? MGR equals MGR plus MGR. Do they all have the same mass? No. Do they all have the same lever arm? No. But when you break them down to simplest terms, don't they all have the same gravitational acceleration? Yeah, so what can we do? G's cancel out. Now you may be thinking, does this happen every time? Why include it in the first place? Go back to that C and part D. You'll be solving for a force, not a mass. And so no, it does not cancel every time, but thankfully it does here. Now we can plug and chug our numbers. And so I'm going to start with the blue. Our mass of the blue is what we're trying to find. Its lever arm is 4. Red has a mass of 6 and a lever arm of 1. Purple has a mass of 2 and a lever arm of 5. So this is why it's easier to figure out the actual force and the lever arms first, okay? But if you hadn't done that, you'd have to do it at this point. And so what do we get here? We get 16 on the right divided by 4. And so if you were thinking the mass equaled 8 kilograms, you're wrong. It equals what? 4. And you're like, but how? The left-hand side, right? It's got that distance reference, okay? It's not about force, it's about torque. Now, before we walk away, I just want to add to this. What about the board itself? Didn't it have mass? It doesn't cancel out. Does this board have weight? Yes, and if you go to center of mass of the board, you would put that force right there at the fulcrum. It has 0. Before torque, you got to have a lever arm, right? And so the lever arm for the rod is what if your force goes through the fulcrum or axis? It has 0 lever arms, so it has 0 torque. That's why I didn't take it into account. But watch out, part B, where's the fulcrum? Is it at the rod's center of mass? No, doesn't the rod itself have a lever arm now? Now, true story. If you're like, but do you have to do the left side and the right side separate? You can. Or if it's a uniform board, just find its total center of mass and use it as an individual torque, okay? You get the same net result. But this is usually what I do. It's easier to do it once than twice. So no, you can't ignore the mass of the board every single time. It just had 0 torque in the first one. Questions?